opposite side of the pattern is beam width, right? Is called beam width. But it means that if you have some pattern like this, and this is your main lobe, so that would be an angular separation between any 2 points. Let's say these are the 2 points. You can say this is beam width. So we have not defined any particular beam width, but we are just saying that what is beam width? It's the distance or angular separation between any 2 points. Okay. So now, what is half power beam width, which we always talk about? So half power beam width is in a plane containing the direction of maximum of a beam, the angle between 2 points in which the radiation intensity is 1/2 value of the beam's radiation intensity, right? So if there's a plane of the maximum lobe or maximum radiation intensity, like I did here, and if this is a half power point of that radiation intensity, then this would be called half power beam width. So previously we were saying that any angular separation between any 2 points on your lobe is the beam width. But if it is a half power point, then it's called half power beam width. And what is first null beam width? So first null beam width is angular separation between first nulls of a pattern. So if in this pattern we talk about what is the first null beam width, it will be, so this is your first null, so it will be this. Right? Okay. So beam width is a parameter, right? But this parameter experiences a trade-off with another design parameter. What it is? So there is a trade-off between side lobe level.
Dr. Khan, what's the word after angular separation between first
Nulls of a pattern.
Okay.
Okay, there's a trade-off between side lobe level and beam width. We know that side lobe levels are unwanted energies in other directions, right? Because we are talking about main lobe. So we want side lobe levels to be very low because we do not want unwanted energy to come out of an antenna, right? But sometimes we want antenna to cover a wide beam, right? So in some antennas, wide beam is another design parameter, like is another criteria. But there's a trade-off between them. So if you want to increase the beam width, you have to wear side lobe levels because they gonna increase. So it's no, they're gonna decrease. But if you want to decrease the side lobe level, then your beam So if your beam width decreases, your side lobe level increases. So let's see what I'm saying. Sorry. So what I'm saying is your side lobe level increase when your beam width decrease. So it's an opposite scenario. Means that for arrays where your beam width is low or your you want a directive pattern, more narrow beam, you want, in that case, your side lobe level will also be greater, okay? It's not for the wide beam, but it's for the narrow beam that where you want, like in the mobile communications we talk about, that if you want narrow beams, then you should expect high side lobe levels. So what I'm saying is for narrow beams applications, side lobe level may be larger because narrow the beam, your side lobe level will be greater. Another thing beams do like that, because you can have several beams of an antenna, or you can control the phase of the beam or the angle of the beam. So beam helps you to resolve the target, okay? So if you are like, if your antenna is on radar and you are sending a signal on the radar, or you are throwing a beam there in air, then if the object is within your beam, then you can see it, right? But if it is not within your beam, then you cannot see that object. So beams are also important, like the width of the beam is also important to resolve the target, okay? So we can say that beam width can also describe resolution capabilities of an antenna. Okay. To distinguish between two adjacent sources or radar targets. Okay. So the most common resolution criteria of an antenna is first null beam width divided by 2. So you can resolve two targets if they are at half of the first null beam width. Okay, so I'll share my screen. Once you are done with this, I'll share my screen to show some slides about this. Okay, so let me know when I can share. Can I share? Okay, 1 minute. So here you can see that these two objects, our antenna is able to see, these two objects, if they are separated by half of the first null beam width. So these two objects, antenna is able to resolve if they are separated by each other by first null beam width by 2. So normally, loosely, first null beam width by 2 means the half power beam width. So if they are separated by half power beam width, we will be able to resolve them. Our antenna is able to resolve them. So this beam width concept is very important because it uses everywhere, wherever we are using antennas. So this is antenna in the radar technology. So you can see this is the wide beam. The two cars are in the region of the, in the middle of the beam. And here you can see that this antenna can resolve only one car. I mean, it can see only one car. So this is the use of the beam in the vehicles. And this is the use of the beam in the radar case. So if you see here, so this is like they are using everywhere. So this is one of the airport traffic control system where they use radars to detect the targets or detect the planes which are coming for different sites. So you can see that in this animation, there are different beams. It's not exactly the case of the airport, but they are sending different beams to see different targets which they can see. So you can see this is very, very narrow beams. And these beams, the narrower the beam, the more targets it can resolve. So that's why we can see many targets. In this scenario, you can see that the target exists near 270 degrees, right? So in this scenario where it's showing the maximum strength of the target is as it is approaching towards 270 degrees, like the antenna's radar. So you can see this blue beam that is going round. So you can see as soon as this beam reaches at 270 degrees, it shows you the target, means that this target exists at 270 degrees, right? And similarly here, you can see that this is the typical scenario of the airport traffic control system or the top normal radars, where these are the continuous wave radars which can move, or you can see that they can move in this direction. So they are actually sending the beams in 360 degrees to resolve the targets. Okay. Do we have any questions regarding that? You're good about it? Michael, what do you think?
I'm good. I'm a little on the left.
Yes.
What do the lines mean? Because they're kind of moving around, like on the little triangles that
This one?
have the different targets. Yeah. What does the direction of the lines mean? Because you can see that they're changing every now and then.
Which lines? Like the
The little
like?
white triangles that have the lines coming out of them.
Oh, so these targets you're talking about, right?
Yes.
These are just, I mean, a simple targets, and they are changing because with time they are changing their direction. So if you are sending beam at t is equals to 0, they may be at some other direction, but you are sending beam at t is equals to 1/2, so their direction is changed. So that's just this, that you can see target moving. It's not like the aeroplane or some other target, but it's just, I think, some example to show how can you see the targets.
Okay.
Yeah.
I have another question.
Mm-hmm.
So the animation in the middle, you
Yes.
can see like that at 270, there's like a blip
Yeah.
on the graph. But on the third animation, like I see there's a scenario where you have two blips, like say at the same degree. How do they manage that? Like in figuring out, like wouldn't it just show up as one pulse on the graph?
Okay. Yeah. So what happens is that that's what we are saying, that if your antenna has a narrow beam, right? So right now this is one continuous wave antenna that is going like that. But if there are two targets here or two planes here, then your antenna, to be able to detect them, it should have a narrow beam. So if they are separated by half power beam width, then you will be able to detect them. Like if you see here in this scenario, so if your targets, if I just can draw it 1 minute, if your antenna sees two targets, then this beam will be like this. You see what my point is here?
Okay, I see.
So it will show that there are two targets, okay, at the same phase, but they should be separated by half power beam width. Are we good about it? Can we move on?
Yes.
Okay, sounds good. Let me stop share and we will move on. Okay, so I will solve what I should say. I will solve example. Okay. Sorry. So I will solve an example in which we will calculate half power beam width. Okay. Okay. So there are two examples in your book related to, no, one example is there, related to beam width, but there are two examples related to the directivity. Okay, let's see. So one more thing I just want to mention, we are saying that half power beam width is normally equal to first null beam width by 2, approximately. Okay, so now I will do an example. The normalized radiation intensity of antenna is represented by where your theta changes between 0 to 90 and your phi changes between 0 to 360. Okay. Okay, can you tell me like what comes in your mind when I say your theta varies from 0 to 90? What I'm talking about? So when I'm saying that my theta varies from 0 to 90, it means that I am talking about only half of the portion, right? I am just saying that if it matters if your like radiation pattern is in something like this. So if your radiation pattern is something like this, then it doesn't matter because your radiation pattern lies between 0 to 90 degrees, right? So if this is your theta. But if your radiation pattern is something that is like this, like the donut shape in which it changes between, your theta changes between 0 to 180 degrees, then it matters because you are just talking about half of the scenario. You see what I'm saying? So just to keep this in your mind that things are important to know. Okay, so we want to know half power beam width and first null beam width. Okay, so let's just try first the half power beam width, okay? So since U theta represent power pattern, so to find HPBW, we will set it as half of its maximum, okay? So it means that theta will be half power beamwidth if cos square theta cos square 3 theta is equal to 0.5. Okay, so theta will be equal to half power beamwidth if your radiation density is 1/2. So if I just take the square root of this, this will become 0.707. So now in this equation, to find the half power beamwidth, you have to apply iterations to see that what is the point where you get this. So something like this, but they have applied iterations to find that at what point you can find out theta h. So theta h comes to be 0.25 radians, which is equal to 14.325 degrees. So it means that this is the angular separation. It's the half power beamwidth, right? Okay, so it's this point. If you see here, so let's say if this is your pattern, so theta h is your point at 14.325 degrees. Okay, but this, you know that theta is the point with zero axis, right? So to calculate the other side of theta, here we are thinking that because this cos function is symmetrical, due to symmetry, you will say that your other theta or 2 theta h will be 2 into 14.325 degrees, which means that it is 28.65 degrees, means your total separation is this thing. So here, this is your half power beamwidth, which will be 28 degrees.
How would you solve for theta n if you have that variable inside like the expression as well?
Yes, I'll tell you. Okay, one more thing is that this is theta h because it's at the half power point. So this is theta h. Okay, and the other thing is that this is they call it transcendental equation. So we can only solve it by iterations. So it's just that you try to figure out that at what point you're gonna get half, like the 0.707 by multiplying that. Okay, so it's like the first point. Let's say you start from 1 degree, okay, or 2 degrees. So you apply, 2 radians. So you start from 2 radians or 1 radians, and after each radian, you're gonna find what the product is coming. So the first radian that gives you the product that is near to this 0.707 will be your half power beamwidth. So you can do easily this with computer by putting the loop in, right? So to find that the first point where you are getting it equals to 0.707. This is the half power angle you have. Okay. For this, not for the first null beam width. Okay. So that one thing I want to iterate is that theta h is the point that this vector is making with your z-axis, right? So to find half power beam width, you have to multiply it with 2. So that's why you are saying that half power beam width is 2 into 14.325. Now, how we can find out? So you are done writing. Okay. Can we move on, Christopher?
Yeah, I got it.
Okay. So let's see first null beam width. Okay, so first null beam width is when your radiation intensity becomes 0, right? So it means that you say now this is n, and that was h, because this is a null. So this is equals to 0, which means that null is equal to 0. I mean, the square root will also be 0. So if you can also write this as so solve for that for which it comes 0. So this is at theta is equals to theta null, and this is theta is equals to theta null, and that will become cos inverse 0, 3 theta cos inverse. No. Yes. So this is equals to pi by 2, and this is equals to pi by 6. All right. So we can say 90 degrees, and we can say 30 degrees. So we solve that cos theta will become 0 at 90 degrees and cos 3 theta becomes 0 at 30 degrees, right? So either of them will be 0. Your radiation intensity will be 0, right? So we will take the first point when your radiation intensity will be 0. So what do you think will be the first point is 30 degrees or 90 degrees?
$30 degrees.
30 degrees, why?
Don't you start from theta 0? So you work her up to 30 first?
Yes, that's right. So 30 degrees is the point where you will take your first null beam width. Yes, Andrew?
I was saying the same thing.
Okay, so 30 degree is the point where your first null beam width will happen, because if you see here, as you move from here to here, so this point will come first and this will come later. So it means that maybe your radiation intensity is 0 at both of these points, but this point will come first. That's why your first null beam width is 2 into 3 theta null, which is 2 into 30 degrees, which is 60 degrees. Okay, sounds good? Okay. So now we will do another parameters. So in this chapter, mostly we are doing parameters, like we are doing radiation intensity, we have done beam width, we have done radiation density. Now I'm doing directivity. So we will be doing all the parameters in the second chapters. So once we will be done with these parameters, I am thinking to do the second chapter before the midterm, like we will finish it before the midterm. So in the second part of your course, we will focus on antenna types, right? So once we will be done, what parameters we should be thinking about, then we will move towards the antenna types. Like maybe we will be doing microstrip antennas and all sorts of antennas. So first we have to be done with these parameters.
Hey, Professor, is there a date selected for the midterm yet or no? Not yet.
What?
Is there a date selected for the midterm or not yet?
Normally what I do is that whenever your midterms are happening, I will, ask date from you guys, like what date suits you, okay? So then we will take like the midterm. So right now your midterms are in the middle of March.
Yes.
In the second week of March?
It really depends on the class.
Yeah, it depends. Like mine's like some of them are the 3rd.
Okay, so when our this class is not happening, it's in the last week of March or the second week of March, or the second last week of March. I have to see that, but I think that let's do it in 3rd week of March. Okay, so maybe so we can do it on 15th or on 18th, right? So what do you think? Yes.
I don't know about everyone else, but I think the 18th would work better for me. I think.
Okay,
around
so
the
1
15th,
minute.
another-
Click on the participant list. Okay, and those who are good with 15th, say yes. Click on the participant list. No, nobody's good for nobody's good with 15th.
I don't quite know yet, like, because a lot of my classes haven't decided on like what the schedule for midterm, so I don't know.
Okay.
I know
So
for me, the 18th would be better because I do have other ones, I think, in the beginning of that week.
okay, so let's see who are saying 18th is better. Do no. Okay. So if I say more no's than yeses,
I might be wrong, but I thought the 18th was one of the days that the schools closed this semester.
oh,
Oh, right, it is.
okay, let me figure out when my classes are not happening, okay? So I think it was the second last week, right? Or they are doing alternative days, I think. Okay, so I will just see. So maybe I want to do it a little bit later, not like the second week. I'm not comfortable with the second week. So So it will be either like whenever after second week, whenever our class will be available, I'll do that midterm, okay? So, but I'll
Thank
tell
you.
you the date exact. Maybe next lecture, okay? And I will do like the take home exam, the final one, but not the midterm. Midterm will be the in class. Okay. So I am doing directivity. Let me share my screen. Okay. So what is directivity? So directivity is, it's a ratio of radiation intensity in a given direction from antenna to the radiation intensity averaged over
Sorry, what's the word in red?
all directions. 1 minute. So ratio of radiation intensity in a given direction from antenna to the radiation intensity averaged over all directions. What word? Third?
The word in red. I just wasn't sure what that said.
Oh, okay.
What does it say?
I will write it a little bit more clearly.
Oh, that's what I
Directivity.
thought it was. Okay.
No, it's good. I mean, it's okay. Okay. Okay, so directivity is the, in other words, we are saying, so if I just write it in the mathematical term, it is U over U naught, okay? Where U naught is the radiation intensity of isotropic source, because that is the radiation intensity that is averaged over all directions. So this is the radiation intensity of isotropic source, or the radiation intensity that is averaged over all directions. So if I just write it, then it can be written as, because we know that radiation intensity of isotropic source was P rad by 4 pi. So if I just replace this here, it will become this. So in other words, you can also say this, that directivity is, and you can say that because it's the same quantity, like intensity over intensity, that's why it is dimensionless quantity. Okay. And you can also, in the simple terms, you can also state it like this, that the directivity is ratio of radiation intensity of non-isotropic source in a given direction over that of an isotropic source. So it's like the yes, isotropic source. So it's like the source that you are calculating the directivity over the isotropic source. So that's what the directivity is. So pretty much, if you see, so you know the radiation intensity of isotropic source is like a sphere, right? So radiation intensity of any non-isotropic source, which has some direction, it will be different than isotropic source. So that ratio is giving us the directivity. We will see an example what is directivity and how we will calculate it. So I mean, this is very obvious, but we just want to write it, that maximum directivity is U max by U naught. Like the maximum point on your pattern where your radiation intensity is maximum will give you maximum directivity, which is very clear. Okay. Okay. Another thing is that we are thinking that if we are calculating the directivity of isotropic source itself, what it should be?
One.
Yes, it should be 1, because that's what the comparison is. So that's why it should be 1. Okay. So we are good about this. Okay, so sometimes it happens that you have multiple patterns in different directions, right? So in that case, you define like the partial directivity. So what I'm saying is that maybe you will learn this. I mean, we will do this later, like what the polarization means, but here just for the definition, sake of definition, I'm writing it. So just don't be confused with that. So in antennas with orthogonal polarizations, we will talk about this, okay? So just for now, you can think that your antennas, there are antennas that are vertically polarized and there are antennas that are horizontally polarized. So those antennas who are vertically polarized, they can send energy only in the vertical direction. So that's the direction of your electric field. And those antennas who are horizontally polarized, they can send energy only in the horizontal direction. So it's related to something with the direction. So that's what I'm trying to say, that antennas with orthogonal polarization, we define, but we will learn about it. We define partial directivity. So just to make it simpler, I can say that D is D theta plus D phi. So it can be possible that your antenna sends energy only in theta direction or only in the phi direction. So depending upon this, it's defined as the partial directivity. So where your d theta is 4 pi u theta by total radiated power, that is in the theta direction or in the phi direction. And your d phi is 4 pi u phi over total radiated power, that is in the theta direction and in the phi direction. But we will talk about polarization. But we just want to say that your directivity is the combination of any directivity that is in some other direction. Okay? Okay. So let's do an example and then we will compare what we are talking about. Okay. So are we clear about this? I mean, we don't know polarization yet, but are we clear about directivity? Louis, what do you think?
Yes, thank you.
And am I fast?
No, you're fine. Thank you.
Okay. So I will do an example for the directivity and I want to do it. It's important to do it. So let's see. So I think we have done this example before. So we will just take the radiation intensity out of this example. So this is example that we have done before in which we said, this is example 2.5. So in this example, we know that our radiation intensity is, as it is taken from previous one. So our radiation intensity was A naught sine theta. And your maximum radiation intensity will be A naught at theta is equals to pi by 2. So we are asked to calculate the directivity. Okay, U max is equals to A naught at theta is equals to 2 pi by 2. And we have calculated our P rad before. That was pi square A naught. So this is all the quantities we are using from the previous example. If I just move to the previous, let me just move here. So we are taking from this example that we have done in the last class, in which our radiation intensity was this one and our P rad was this one. Okay. So I'm just using the same thing. Okay, so P rad was this. So our maximum directivity, yes, so D max will be 4 pi into U max by P rad, which will be 4 pi into pi by 2 . No, sorry. 4 pi into A naught by pi square A naught. So yes, so it will be 4 by pi, which is equals to 1.27. So that is your maximum directivity. And your normal directivity is So you can see that this is something that is greater than 1, right? So if it's not an isotropic source, it's a source that is giving you more than 1, like the directivity equals to more than 1. So it means it is directive than isotropic source. So we will compare this with another equation that we are doing. So let's do another example to compare this directivity with another directivity, okay? So let me do it. So are we good about this? Keith, what do you think?
Yeah, I think I'm doing okay.
Okay. So, okay, so let me do another example. So this example is pretty much solved in your book. So I want to do it because I just want to compare it. So maybe I will skip some steps, but it's already there in your book, okay? So it's example 2.6. So in this example, you are given a linear dipole's average density. Okay, so this average density is so let's compare this average density with the density we solved before, okay? So this is our density A naught sine square theta over R square. So let me see what was our average density before. So previously our average density was A naught sine theta over R square, right? So this time the difference is that we have square theta in it. Okay, so we want to see what square theta, like what difference square theta will make. Okay. Okay, so we are asked to calculate maximum directivity and express the directivity as a function of theta and phi. So to calculate maximum directivity and directivity as it is, we want to know radiation intensity, which is R square WR, which will become A naught sine square theta. Okay, then again, we know that U max will be at theta is equals to pi by 2, which will make it A naught. Okay, so we don't know P rad in this case. So my P rad will be A naught sine square theta, solid angle. What limits should I put here? If I'm not given any limits, what limits should I put?
0 to 360.
0 to 360 is the limit of?
For the phi.
Yes.
And then 0 to pi for the theta.
Right. That's right. Okay. So these are the limits I'm going to put. So that is becoming sine cube theta. And I'm not solving the integral of cube theta. You can find that out. So the answer is 8 pi by 3 A naught. Okay, so it means that the integral should come about 4/3 because 2 pi is coming from phi. Okay, so it's a naught 8 pi by 3. So our directivity will be 1.5, right? So what do you think that in this scenario, directivity is more than before or less?
Isn't it more?
Yes, the directivity is more. And we want to also know, so this was the maximum directivity. We also want to know the directivity that is not maximum, that is the normal directivity. And that will be right? So the difference now you can see here, I want you to write first, and then we will talk about it. The difference you are seeing here is this directivity with this directivity, like this one. So you can see that in this you have sine theta, and in the other case you have sine square theta, right? So we will see what the difference will be between them. But just keep in mind that from the maximum directive point of view, we know that the second is more directive than the first one, okay? But now we will see how this directivity affects. We are good till here now? Okay, so let me share my screen to make one more point, okay? So here, this is the thing we are talking about here. I cannot see my mouse, okay. So this is the thing we are talking about. So this is the pattern of sine square theta, and this is the pattern of sine theta, right? Right now, 1.5 means that so they actually normalized it. That's why it is at 1. But normally, if this is the more point, so it should come here, somewhere here, like the more directive thing, and this should be lesser than that. So something like that, okay? So this would be your 1.5 point, sorry, 1.27 point of the maximum directivity, and this would be your 1.5 point. So because these are what you should say maximum at theta is equals to pi by 2. So means that this is the point where we are seeing the maximum value, right? Because this is theta pi by 2. Or this is also the maximum point because this is also theta pi by 2. So at phi, at any point where theta is equals to pi by 2, you are seeing a maximum directivity. But here, this is a normalized version just to show you what would be the shape of sine square theta and theta will be. But let me show you another thing. if you see this one, right? So this is the comparison of isotropic radiator and radiator with the directivity, right? So if you see here, so this is your isotropic radiator with directivity equals to 1, right? And this is your isotropic radiator, non-isotropic radiator, which has directivity equals to 1.67 sine cube theta. It's even more directive and even more thinner than the previous two, like 1.27 and 1.5, right? And what do you think is the maximum point of this one? What angle, at what angle? Bryce?
Would you be able to repeat what you said for me?
I'm saying, what is the maximum directivity of this dipole?
Wouldn't that just be like you substitute theta for 57.44, or am I?
So what is the maximum value of this dipole? If I just put 57.44, it will not be the maximum value, right?
Oh, it would just be 1, right? Like you substitute theta for 90.
Yes, you substitute theta for 90. So what will it comes? This one. Can you see my laser pointer?
Yes, I can.
Yes, so if I replace theta is equals to 90 here, what will be the value?
It would just be 1.67.
Yes, right. So, and when you put theta is equals to 90, at what point should you point it here in this red, blue, and everything? What would be the maximum point?
It would be in the red.
Red, but red covers a lot of angles, right? So what exactly at what point should I say that this is my maximum directivity?
The red at the 90 at the very edge of the
yes,
bulb.
So this is your maximum directivity point, right?
Yes.
Right. So just I want to make it clear that that's the difference between your isotropic radiator and your non-isotropic radiator, right? So if you move, thank you, Bryce. So if you move here, another way of looking at it is this. So this is your isotropic radiator, right? Like the Sapphire one, but this one is your non-isotropic radiator. So you can say that your non-isotropic radiator is less directive in this region, where in this region, before it's half power beam width, right? But it is more directive in this region, right? So like they are mentioning that it's half power beam, which starts at 57.44 and it goes to 122.56. So it is less directive before this point and after this point, but it is more directive in this point, right? Another thing you can see that its maximum angle is 1.67, right? And, oh, sorry, not maximum directivity is 1.67, which happens at theta is equals to 90 degrees. So are we clear about this? John?
Yeah, it's clear.
Yeah. Oh, yeah.
Okay. So I think I will stop here, and so I did not upload minute paper today, but I will upload it in a minute. So you can go after some time to access it and write it down. And that's about it for today. Thank you.
Have a good day.
Thank you. Have a nice day.
Bye.
Have a good one.
Thank you, everyone.